Hello, this is Tahsin from Roots of Unity, bringing to you the magic of matrix multiplication. However, before we get started into matrix multiplication, we must know a little more about the dimensions of a matrix. The dimensions of a matrix refers to the height and width of a matrix. The height refers to the number of rows a matrix has, and the width refers to the number of columns the matrix has. And we write all this information in the shorthand denotation of HXW, where H refers to the number of rows the matrix has and W refers to the number of columns the matrix has. Let's look at a few examples to make that clear. Let's say we have this matrix 2 0 0 2. This matrix has 2 rows and has 2 columns. So we will write this down as 2x2 in the shorthand denotation. This 2 refers to the number of rows and this 2 refers to the number of columns. Now let's look at another example. Let's say we have this matrix 1 2 0 2 3 2. This matrix has 2 rows and has 3 columns. So in the shorthand denotation we will write this down. We will write the dimensions of this matrix down as 2x3. This 2 telling us that the matrix has 2 rows and this 3 telling us that the matrix has 3 columns. The reason why we took some time off to learn about the dimensions of matrices is because you just can't multiply two matrices just like that. Two matrices have to be compatible with each other in order to be multiplied. And whether or not two matrices are compatible depends upon the dimensions of the matrices involved in the multiplication. Two matrices are compatible with each other and can be multiplied together when the width of the first matrix is equal to the height of the second matrix. If these two numbers are the same, then they can be multiplied together. Let's look at a few examples. Let's say we have these two matrices. This matrix has 2 rows and 2 columns, and this matrix has 2 rows and 2 columns. We can see that the width of the first matrix is equal to the height 2 of the second matrix. Since these two numbers are equal, these two matrices can be multiplied together. Let's look at another example. Let's consider this 3 by 2 matrix and this 2 by 2 matrix. The width of this matrix is equal to the height of this matrix. Both of these numbers are 2, and hence these two matrices can be multiplied together. Let's look at another example. Let's say we have these two matrices, this 3 by 2 matrix and this 1 by 3 matrix. The width of this matrix is 2 and the height of this matrix is 1. 2 and 1 are not the same and these two matrices cannot be added together. However, if we switch these matrices, if we switch the places of these matrices, you can see this matrix would be 1 by 3 and this matrix would be 3 by 2. The width of this matrix is 3 and the height of this matrix is 3. This number and this number is same, and hence these two matrices can be added together. So you see, sometimes it may seem that two matrices can be multiplied at all, but if we just switch the places up and multiply it in the other order, we can actually find out that the two matrices can be multiplied. So it's usually best practice that whenever you can't multiply matrices in one particular order, you switch the matrices and check whether they can be multiplied from the other way around in the other order. Before we get started into matrix multiplication, there is another important thing that we must see. When we multiply two matrices, it forms another matrix which has the height of the first matrix as its height and the width of the second matrix as its height. And now that we are done with that, let's look at actual matrix multiplications. Let's say we have these two 2 by 2 matrices here. These two matrices can be multiplied with each other since this number is equal to this number, and would form the matrix and would form a 2 by 2 matrix since the height of the first matrix is 2 and the width of the second matrix is 2. So how do we multiply this matrix to this matrix? We multiply them by multiplying this row to this column. And how do we do that? We multiply 1 to 5 and multiply 3 to 6 and then add these two terms together to get our result. And we place this number in the first row of the resultant matrix and the first column of the resultant matrix here, like this. and then we multiply this row to this column here. And how do we do that? We multiply 1 to 7 and 3 to 8 and add those two terms together to get 31. And we place it to the first row of the resultant matrix and the second column of the resultant matrix. And then we multiply this row to this column here, and we do it by multiplying 2 with 5 and 4 with 6, and then adding those two terms to get 34, which has to be placed in the second row and the first column of the resultant matrix. And then we multiply this row to this column, 2 being multiplied with 7 and 4 being multiplied with 8, 2 into 7, 4 into 8, and then we add these two terms together to get 30, which would be placed in the first row and the second column, of the resultant matrix. Now let's look at another example. Let's say we have this 3 by 2 matrix and this 2 by 1 matrix. These two matrices can be multiplied and would form a matrix with the dimension 3x1. So how do we do the multiplication? We multiply this row to this row, so we get 1 into 1 plus 4 into 0, which gives 1, and then we place this 1 in the first row and the first column. It gets placed here. And then we multiply this row to this column, so we multiply 2 into 1 and 5 into 0 to get 2, and this 2 would be placed in the second row and the first column, first column. And then we multiply this row to this row, 3 into 1 and plus 6 into 0 to get 3, and this 3 would be placed in the third row and the first column. Now let's look at one final example to end it all. Let's say we have this 2 by 1 matrix and this 1 by 2 matrix. These two matrices can be multiplied together, since this number and this number is equal, and would form the matrix with the dimensions 2x2. And how do we multiply it? We multiply the first row to the first column first, which is just 1 here and 2 here. So we do 1 into 2 to get 2 and place it in the first row and the first column. And then we multiply the first row to the second column to get 1 into 3, which is equals to 3, and place it in the first row and the second column, of the resultant matrix. And then we multiply the second row to the first column to get 0 into 2 equals 0. And then we place this 0 in the second row of the first column, And then we multiply this row to this column to get 0 into 3 equals 0. And we place this 0 in the second row and the first column, second row and the second column, the 0 to be placed here. Now that we've seen how matrix multiplication works, we must come to appreciate a very important rule in the world of matrix multiplication. It's such that if you have two matrices A and B, if you multiply A to B, it does not produce the same result as B to A, given that A and B are not the same. What that means is that, let's say you have two matrices, 1, 2, 3, 4, and 5, 6, 7, 8. And you multiply these matrices in this particular order to get the result as 23, 34, 31, and 46. Now, if we switch this matrix and this matrix, if we put this matrix first and this matrix second, and then perform the multiplication like this, if we perform the multiplication like this, we get the result 19, 24, 43, and 50. This matrix and this matrix is no way the same. And you see, by just switching the places, we get a completely different result. So when we multiply matrices together, the order of the matrices is very important and would give you different results. However, there are some exceptions to this rule. The two exceptions to this rule are zero matrices and identity matrices. Zero matrices are matrices which have the same number of rows and the same number of columns and has zeros in all its cells. Let's see what happens when you multiply a matrix to a zero matrix. Let's say we have this matrix 1, 2, 3, 4. We multiplied with the zero matrix and get the result as 0, 0, 0, 0. Now let's switch these matrices up. Let's put the zero matrix in front and this matrix at the second position. Now after performing the multiplication, we see that we got the same result as 0, 0, 0, 0. So no matter which matrix you multiply with the zero matrix, and no matter what order they are in, you will get the same result, a bunch of zeros. Now let's look at the second exception to this rule, identity matrices. An identity matrix is a matrix which has the same number of rows and the same number of columns, whether it be 2, 2 or 3, 3, and has ones in its diagonals. It has the number 1 in its diagonals, and the other cells are filled with zeros, like this 2 by 2 matrix. In this diagonal, you can see that there's a 1 and a 1, and the other cells are filled with zeros. And in this 3 by 3 matrix, you can see that this diagonal is filled with 1, 1, and 1, and we have the other cells filled with zeros. So this is a 2 by 2 identity matrix. This is a 3 by 3 identity matrix. There is also a 4 by 4 identity matrix which has 1, 1, 1, 1 here, 0, 0, 0, 0, 0, 0, like this, and 5 by 5, 6 by 6, and so on. You just have to remember that the leading diagonal of the identity matrix are a bunch of ones, and all the other cells are zeros. Let's see what happens when you multiply an identity matrix with a normal matrix. When you multiply a matrix with the identity matrix, you get the same matrix as the result. So here we multiply 1, 2, 3, 4 to the identity matrix 1, 0, 0, 1, and we get the result as 1, 2, 3, 4, the same matrix as this. Wow. Now let's try switching the place up. Let's put this in front and this in the second position. And now after performing the matrix multiplication here, we get the same result as 1, 2, and 3, 4. We get the same result here, and hence we can deduce that when multiplied with identity matrices, matrices don't follow the rule that AB is not equal to BA. And we must come to appreciate that this is a very special matrix, 1, 0, 0, 1. That's going to be all for matrix multiplication. Next week we're going to be doing inverse matrices. Hope you liked the video. Stay tuned and stay curious. Signing off, Tahsin.